Hello everyone, my name is Maya Chertouni, and with Thomas Cluzot and Alban Quadrat, we worked on the algorithmic study of the algebraic parameter estimation problem. Here is the table of contents. So first I'm going to give the motivation. Then we will talk about the inverse Cauchy problem for linear ordinary differential equation. Then we will treat the more general case, which is the algebraic parameter estimation problem, then the implementation, and finally the conclusion. Let me first begin by giving a simple example. So if we consider that we have a sinusoidal signal, which is A times sinus of omega t plus phi. The question here is, can the amplitude, the phase, and the frequency be expressed in terms of x of t and its iterative indefinite integrals? This is a problem that has been studied for a long time in control theory and signal processing, and there is a lot of methods that deals with this problem. But in our case, we treated the new approach developed by Fliess and Sira-Ramirez in 2003. And our contribution was the algorithmic study using computer algebra methods. So basically, this approach consists in considering the ODE satisfied by the signal, which is in our case the equation in black, where A0 is equal to omega square, and then to take its Laplace transform. But first, let us recall that the Laplace transform of x can be rewritten as x hat, and the Laplace transform of x prime is equal to s times x hat minus x of 0. So in the frequency domain, we have that x hat satisfies the equation in blue, where v0 and v1 are the initial conditions. So we have v0 is equal to x of 0 and v1 is equal to x prime of 0. Now, if we estimate V0, V1, and A0, we can go back to A, omega, and phi. We notice that we have in V0 and V1 polynomials of degree 1 and 0 respectively. So if we differentiate once, we can recover V0 and V1 and we obtain the following system. So now we have to go back to the time domain. So we have to apply L inverse. But we notice that V0 and V1 are polynomial in S of degree 2 and 3 respectively. And if we apply L inverse, we will get V0 and V1 in terms of x of t and its derivative, since positive powers of S give derivative of x when applying L inverse. And we don't want that. We want to get the expression in terms of integrals of x. So for that, we have to get negative powers of s. And that's why we rewrite V0 as n0 over d0, where n0 is equal to V0 over s cube, and d0 is equal to 1 over s cube, and V1 is equal to n1 over d1, where n1 is equal to v1 over s to the power 4, and d1 is equal to 1 over s to the power 4. Applying L inverse, we get the following expression that contains convolutions. And since V0 is a constant, we have that V0 is equal to Laplace inverse of N0 over the Laplace inverse of D0, and same for V1. We still have A0 that is unknown, so we still have to estimate A0. If we go back to the equation in blue, and if we differentiate 2 times, we can eliminate V0 and V1, and hence we can recover A0. So we get the following expression that we rewrite as n over d, where n is equal to A0 over s cube, and d is equal to 1 over s cube, and then we apply the L inverse to get A0 is equal to L inverse of n over L inverse of d. So now we have the explicit expression of A0, V0, and V1, and we can go back to omega A and phi using the formulas in blue. And we can verify that if we replace x of t by A sinus omega t plus phi in the expression, we get omega square x of 0 and x prime of 0. In general, We don't observe only the signal, but we have a signal that is corrupted by a perturbation and a noise. So we have x of t plus gamma of t plus varp of t, where gamma is the perturbation and varp is the noise. And I insisted a lot on the fact that we want to have integral of x in the above expression and not derivative of it. And it is because when we integrate, we can filter the noise. In the first place, we will consider that that gamma of t is equal to varp of t is equal to 0. So we are going to study the exact case, which is important because if we can solve it, we can solve the problem in the general case. So let us consider that x satisfy the ODE in blue, where AI are polynomial in T with coefficient in Q, and let us assume that A and 0 is not 0, so 0 is a regular point of the ODE. The Cauchy problem is, given an ODE and initial condition, can we study the existence and uniqueness of the solution? But in our case, we treated the inverse Cauchy problem, which is given a solution x, can we find the coefficient of the ODE and the initial condition? So first I'm going to give a recall of the Laplace transform. So as I said, we can write the Laplace transform of x as x hat, which is equal to the integral from 0 to infinity of the exponential of minus st times x of t dt. And it satisfies the following properties. The Laplace transform of derivative of x is equal to powers of s times Laplace of x minus the summation of powers of s times the initial condition. Laplace transform of powers of t times x is equal to derivative of the Laplace transform of x, and Laplace inverse of f hat times g hat is equal to f star j, where the star denotes the convolution. So if we apply the Laplace transform to the equation in blue, and we use the properties I just mentioned, we can show that it gives us in the frequency domain the equation in black. So if we note now P this by the summation of AI minus partial SSI, Sk the summation of AI minus partial S to the power I minus K minus 1, Vk the initial condition, and theta the vector of the initial condition, we will get that the equation in black is P times x hat plus the summation of Sk Vk is equal to 0, which also can be rewritten as the equation in red. We showed that Sk has a degree of n minus k minus 1, since the valuation of an in 0 is 0, so 0 is a regular point. And now if we differentiate n minus 1 times the equation, we obtain s times theta is equal to minus p and derivative of p times x hat. We notice now that S is an anti-triangular matrix with determinant non-zero because A and 0 is not 0. So we can compute the inverse of S, and hence we can recover theta, which is the vectors of the initial condition, and thus the VIs can be expressed in terms of x hat, its derivative, and the coefficients of the ODE. And now we have to go back to the time domain. We showed that the degree in S of Vi is equal to n plus I, so we rewrite Vi as the quotient of Ni over Di, where Ni is equal to Vi over S to the power the degree of S in Vi plus 1, and Di is equal to 1 over S to the power n plus I plus 1. And then we apply L inverse, and since Vi is a constant, we have that Vi is equal to L inverse Ni over L inverse Di. We still have to estimate the AIs. So we recall that AI is a polynomial in T with coefficient in Q, so it can be rewritten as the summation of Aij Tj. So we still have to estimate the Aij's. If we go back to the matrix in blue, And if we differentiate, we can eliminate all the VI's. So for L greater than N, we have equation that does not depend on the VI's. So we get the matrix in red times x hat times A is equal to 0, where A is the vector of the Aij. Assuming now that A and M is not 0, and let us write P by the number of unknowns of Aij. L is P minus 1. See the matrix in red without the last column. See the last column of the previous matrix. B, the vector A without its last component. So we get the equation in black. Now we have two cases. The first one, if the determinant of C times x hat is not 0, then we can compute it inverse, and then we can recover B. So we can recover all the Aij that we rewrite as Nij over Dij by dividing with a good power of S, and then we apply L inverse to find the explicit expression. Now, if the determinant is empty, then we have showed that X verifies an ODE of a smaller order or degree. So we say that X is a non-generic solution of the ODE. So in this section, we have showed that if x of t is a generic solution of the ODE and t is a regular point of the ODE, then all the initial condition and the coefficients can be expressed in terms of x of t and its iterative indefinite integrals. We still have to treat the non-exact case, but it's still under development. So first I'm going to give an example about it. So if we suppose that we have a signal that is corrupted by a perturbation, so we have x of t plus gamma, where x of t is equal to a times sinus omega t plus phi, and gamma is a constant, so it's a bias. Applying the Laplace transform, we obtain the equation in black, where a0 is equal to omega square. V0 and V1 are the initial conditions. Here we have gamma that is unknown, so we have to get rid of it, and then we can proceed as before to compute A0, V0, and V1. So if we write Q bar as S square plus A0, we can compute its annihilator to eliminate Q bar, and hence we can eliminate gamma. And we can compute the annihilator using elimination technique and Grobner-Basis techniques. So after computing the annihilator, we use each operator and we apply it to the equation in black. And hence we can recover A0, V1, and V0 that we rewrite as Ni over Di by dividing by the appropriate power of S. So we can recover their explicit expressions. And we can go back to omega, A, and phi by using the formula in blue. Now I'm going to give some result of this section. Let Z be equal to the signal X plus the perturbation gamma. In the frequency domain, we get the equation in blue. So we have here gamma unknown and R and Q defined as before. We consider a perturbation of the form gamma of t is equal to gamma times t to the power r times the Heaviside function. So when we apply the Laplace transform to it, we get gamma over s to the power r plus 1. The last term of the equation in blue can be rewritten as the summation of a polynomial in S inverse and a polynomial in S. So let us set P the degree in S inverse of gamma S gamma S inverse. So now if we multiply the equation in blue by S to the power P to eliminate the denominators, we get the equation in red. Now we rewrite a Q bar as the summation of bk s to the power k, from k equal to 0 to q, where q can be bounded in terms of r and the valuation/degrees of the AIs. We want to compute the annihilator of this polynomial to get rid of gamma that is unknown. We showed that the annihilator of q bar can be generated by p1 and p2. Okay, so now we use p1, the operator p1 that we apply to the equation in red. So we will get the equation in black, and by definition, the last term will be equal to 0. Now, if we have the degree of the polynomial p1 times sp times sk is equal to p plus ek, where ek is the degree of sk, and 0 is a regular point of the ODE, then we can express all the vk's in terms of z, its iterative indefinite integrals, and the aij's. And then we rewrite it as quotient by dividing by the good power of s, and we apply L inverse to get the explicit expression. Now we still have to estimate the aij's. So for that, we apply P2 to the equation in red, and we get the equation in blue. And if we denote by V the maximum of Q plus 1 and the degree in S of S, and we apply it to the partial of S to the power V to the equation in blue, we will get the equation in green. So we got rid of all the VI's, and hence we get the equation in green. And now we differentiate enough to get the matrix in black time Laplace of z is equal to 0. And hence we can proceed as before to estimate the aij's in terms of z and its iterative indefinite integrals. In our study, we used a lot Maple and the package NOAA, which is dedicated to the actual study of the algebraic parameter estimation problem. Its main commands are listed here, and we used a lot of Maple packages. We developed this package by adding some functions that are useful, and we have developed several examples, such as the sum of sinus, sum of exponential, and I have added an example in the last part of this PowerPoint, but I don't have time to talk about it. So finally, using algebraic differential and computational methods, we have studied the inverse Cauchy problem for a class of ODE, and we have started to extend this result to the case with perturbations, but we still have to treat a more general classes of perturbation. And what we would like to do also is to continue to develop the package NOAA. And finally, we can use another approach, which which does not consist by taking the Laplace transform of the equation, but only only to stay in the time domain, and it is called the integral differential calculation. Thank you for your attention.